Okay, 4.1, Extrema on an interval. So let's look at this problem. For the function below, f of x equals x cubed minus 3x on the closed interval from -3 to 3. Find x where the derivative of f of x equals 0. So let's do number 1. So they want us to take this function and figure out the x values where the derivative of f of x equals 0. So the first thing I have to do, I have to take the derivative of this function, which this should be an easy derivative for us by now. This would be 3x squared minus 3, power rule. Okay. And then what we need to do, we need to take this derivative, set it equal to 0. And here you can see we can factor, so this would be 3 times x squared minus 1, which would be equal to x minus 1, x plus 1. Thus, x must be equal to 1, and x must be equal to -1, right? If you would plug in 1 there, that would give us a 0. Plug in -1 there, that would give us a 0. So this is for number 1 here. Part A here, what do you notice about where these x values occur? Okay, if you look at this graph, this is where these x values occur. These are known as turning points. Okay, so the slope of the tangent line is going to equal 0 at turning points here. The slope here is increasing, and then it hits the turning point, and then the slope here is decreasing, hits the turning point, and then the slope here is increasing. Okay, so we answered that. Find the minimum and maximum value of f of x on the closed interval. Okay, so this value here and this value here, this would be a relative max, and this would be a relative minimum. Okay, so for f of 1, this would equal 1 cubed minus 3 times 1, which would be 1 minus 3, which would be -2. Okay, so that's right here. This is a relative minimum. And then f of -1 would be -1 cubed minus 3 times -1, which would be -1 plus 3, which would be 2. This would be a relative max. We'll talk more about what this relative max and what relative means in a minute. Also, what I want to do, I want to test the endpoints. Okay? This graph, it's been restricted between -3 and 3. So notice when x is -3, this would be -3 cubed minus 3 times -3. Well, -3 cubed is -27. -3 times -3 is +9, so this would be -18. And 3 cubed minus 3 times 3, this would be 27 minus 9, which would be 18. So at -318, this would be the actual minimum value. Okay, and at 318, that would be the absolute max value. Hopefully that makes sense. Okay, so you got relative min at 1, -2. You got a relative max at -1, 2. you've got the absolute max, which you just call max, which is -3, -18, and you've got a max at 3, 18, because 18 is the largest value on that domain. All right, so let's look at some definitions here. Definitions of extrema. Let f be defined on an interval I containing c. Okay, so extrema is either a max or a min. Okay, if f of c is a minimum of f on some interval I, then f of c is less than or equal to f of x for all x in I. So here is an example here of a minimum value. This would be the minimum value here. This is the smallest value on the function. Every other value on this function is greater than f of c or equal to f of c. Okay? The maximum definition is very similar to the minimum definition. Extreme value theorem, okay? What the extreme value theorem says, it says if f is continuous on a closed interval ab, then f has a minimum and a maximum value on that interval. Okay, so anytime you have a function that has a closed interval ab, okay, there's going to be both a maximum and a minimum on that interval. So again, maximum and minimum, those are the extreme, or the extreme values. Okay, definition of a critical number. Let f be defined at c if f prime of c equals 0, or if f is not differentiable at c, then c is a critical number. Okay, so definition of a critical number, f prime of c equals 0. Okay, so it's the c value that makes this statement true, or when f of c does not exist, again, it's the c value that makes that true. So that's the definition of critical values. Critical values are going to be important because typically minimum or maximums can happen at critical values, or relative mins and maxes can happen at critical values. So we're going to find those critical numbers quite a bit. Okay, so here is an example where f of c does not exist. Okay, so that's the c value where that f prime of c doesn't exist, but that would be a max. Okay, here is an example of where f prime of c equals 0, so at that c value you would have another max there. Could be a min depending on the problem. Okay, critical numbers of x values where f prime of x equals 0 and f prime of x does not exist. Okay, now we're going to move on to definition of relative extrema. So there's a difference between relative extrema versus extrema. Let's go look back up here. Okay, this would be a relative extrema. This would be a relative extrema. It's not the absolute max. It's not the absolute min. Where this would be an extrema. Because it's the minimum value of this function. This would be an extrema because it's the maximum value. This would be a relative extrema. Okay, so the formal definition here, if there is an open interval containing c on f of c is a maximum, then f of c is called a relative maximum of f. Or you can say that f has a relative maximum at C, comma f of C. 2, if there is an open interval containing C on which f of C is a minimum, then f of C is called a relative minimum. Or you can say that f has a relative minimum at f comma f of C. Okay, so if all this is saying is if you have an open interval, so if you look at this function here, okay, the domain is an open interval. It's from negative infinity to positive infinity. So you're not going to have an absolute min or max. Okay, we can't say that the max is at negative or positive infinity, because that's a concept. That's not an actual number. That's the idea that numbers just grow without bound. Okay, but we would have a relative max and a relative min. Okay, one more theorem here. Relative extrema occur only at critical numbers. Okay, so again, what I was saying earlier, critical numbers are going to tell us where the relative extremas are. Okay, so if f has a relative min or relative max at x equals c, c is a critical number. Okay, if it's a critical number, that means there is some c value such that f prime of c equals 0, or f prime of c does not exist. Okay, guidelines for finding extrema on a closed interval. Alright, we'll go over this next because this is what we're going to do for the next problem.